just for a face to see. I'm Norman D. Snowden, retired civil engineer and developer of several Mykinda software programs. The subject video is one of the features of Mykinda Traverse. It provides mathematical tools that a surveyor or contractor can use to define horizontal and vertical curves when the direction, that is, bearing of a highway or driveway is changed. Other additional highway engineering functions are described in later videos. The angular difference between the initial direction of a highway and the subsequent direction is called delta. The other factor is the degree of curve or radius. The program allows you to select an arc distance, the distance between points on the curve called stations, and from this, calculations provide the distances and angles to points along the curve. A picture of the curve is plotted showing the bearing and subchord distance between each arc. A printout summary of all curve properties, angles, and distances necessary to lay out the curve is shown. Another method is provided that allows laying out a horizontal curve by using x and y tangents. This is done by simply measuring an x distance along a line tangent to the curve, and at point x, then measuring at 90 degrees a calculated y distance to a point on the curve. This procedure is very useful if the desired radius is too large to allow simply swinging a tape from the center of the circle, or if obstacles would prevent this. Highway vertical curves are calculated based on an approach straight grade, an exit straight grade, the elevation of the beginning point, and the desired length of curve. A screen printout is provided. My email address is duluth@msn.com. After viewing this video, if you have further interest in Mykinda Traverse, send me an email. Subject: Mykinda Traverse. Thanks. We click on the little icon, Mykinda Traverse. We have to agree to abide by the rules of the program. Yes. We're user number 1. There are can be six users. The main program screen comes up. Let's expand this a little bit. Let's start a new record, for this curve. So we will click on Add a Record. It comes up blank. Let's call it Highway Curve, HwyCurve. It's completely blank. We have to follow this sequence closely to lay out a curve. First of all, we want to set the direction of the highway before the curve is started. So let's just use north, 0 degrees, 0 minutes, 0 seconds, and we didn't put the N in, and east, and then we put a plus, which means that the movements, deflections will be to the right. Now we have to we'll use a delta of 45 degrees. This highway is going to change to 45 degrees, so we put in 45. And the radius, we'll use 600 feet. 600 feet. And we'll use an arc distance of 50 feet. And now we'll click on deflect angle. That will start the ball rolling. So we had with the subchord is 49.99 feet. It's just a tenth of a foot, a hundredth of a foot less than the arc. Up here, we should read this info, but I don't think we'll take the time to do it. Put in the check mark here and click on curve convert degrees. We have a message that asks if this is the start of a curve. We'll assume it is. We're not in the middle. Yes. So we see that the first point one, this chord, subchord, is 49.99, and this is the bearing. But we also see an azimuth. From here on, only azimuths will be calculated, and later we will convert them back to north and south bearings. So we click again on curve, double click. And we see another point two. Double click again. Point three. We're down to station 100. Click again. Double click. Now we're down to point four. Double click again. We're down to point five and the station is 200. Click again. Down to point six on the curve. Double click again. Point seven on the curve, down to 300. Station 300. Double click again. Now we're down to point eight, 350. We double click again. We're down to point nine. It's a little deceptive. We've actually moved 450 feet from the point of beginning, even though the station don't reflect that, because we started with a zero distance. Now then, we see that the length of this curve is 471.24 feet, and we're down to 400. So we will set a new arc length. Let's set a new arc of 21.24. 21.24, and click on deflection angle. That's what drives this. Now we see the subchord is 21.94. This is so close that there's actually no difference to the nearest hundredth. So now we'll click on curve, double click. Now we see that the distance is 21.24 feet, and the azimuths are all out here. Now here's something that's important. This will, after this curve is laid out, there will be a return from point, the last point back to the first point. So we have to put in some distance to make it realize that it has to plot this return line. You could use any distance here. But we'll use 100. Now, in order to calculate the curve, we have to change these azimuths to points on the curve. So we click on azimuth, and it says click yes to transfer azimuth angles to the north-south bearing column. We do. There, there they are. That's the bearings, north and south. Now let's calculate that. It'll take a while to compute all that. Properties of the curve are shown down here. The mid ordinate is 45.67, and the length of the curve 471.24 feet. The tangent to the curve is 248.53 feet. We're still waiting on this calculation. Down here you can add angles using minutes and seconds, and you can also multiply angles using minutes and seconds. Still waiting for calculation. There, it's done that. Well, I miscalculated here. This that should no, I didn't. This 44.997, that's 45 degrees. This station is 421, but it actually, you have to add the 50 to it, and it will come out as 471. It's actually, but the length of the curve is 471.24 feet. Let's click plot. So there we see this curve. Each bearing and distance, but then there's a tie that goes back to the point 1. It's south 24 degrees, 49 minutes and something. This area here could be considered as an area that should be kept clear for vehicles coming around this curve, so they can see everything is coming. In other words, if trees and so forth are in here, then you're blocked. So that's just an ideal. This is the chord, each chord cumulative, and each angle from point 1 to the other point on the curve. We can look at a summary of all of this if you wanted to go into the field and plot it. I mean, that is stake it out. This is horizontal curve data. The radius 600, delta 45, length of the curve, tangent, mid-ordinate, and deflection angle, and subgrade for this last arc, 21.24 feet, subchord. So you could set your transit at point 1 and using distance and angle and lay out this curve. we could lay this out by, as I said, tangent offsets. We click this use deflection angle for XY tangent offsets. If you put in an X distance for the 600-foot curve, say put in that X distance of 50 feet, and click on X, and double click this no, I wasn't ready for this. Didn't intend to go to that. I'm not as familiar with this as I should be right now. The 50 feet. Deflection angle is what I should have clicked on rather than this other. So it's for 50 feet, the Y distance is 2.09 feet. And the chord out there is 50.04 if you were had a transit set up on the beginning of the curve. That would be the distance you would measure and the angle that you would turn, 2 degrees, 23 minutes, and 24 seconds. Now let's put in 100 feet and click deflection angle. Now we see that Y distance is 8.39 feet. The chord length is 100.35 feet and the angle is 4 degrees, 47 minutes, 49 seconds. If you wanted a series of that, this 100-foot, 600-foot curve, I double click this X. Now, we enter a radius. This would be an independent curve. We enter a radius and a distance interval, say 25 feet, and an X value would say is also 25 feet. Calculate. Now we see a layout of that. For this X distance of 25 feet, you get these Y distances, chord distances, and angles to turn, all up to 600 feet. This would be every 25 feet. Most people would not use tangent offsets to lay out a curve of this magnitude, but it could be done easy enough. We could print that, but we don't want a copy of it. So we go back home. If we wanted to if we wanted to double this, we'll say that this is 1 degree, 0 minutes, and 50 seconds, and we want to multiply by, we'll say 2. Double click. And we see that it's 0 degrees and I used point two. I mean two. Now it's 2 minutes, 2 degrees, 1 minute, and 39 seconds. By the same, up here we could actually add angles. If we put in we had 0, 0, 0 here. Let's put in, want to add 2 degrees and 10 minutes and 30 seconds. Double click equal. Well, that's times 0. Normally you can't multiply it by 0, but in this particular setup you can. We had 2 degrees. No, this, I'm sorry, this 0 had nothing to do with that. We just multiplied 210 times 210. Let's try something else. Let's try, we added, let's add 4 degrees, 4 degrees, 30 minutes, and 45 seconds. Well, I guess we have to add this from back here. There you go. Say we added 2 degrees, 30, 30, and 30, plus this 4 degrees and 45 minutes. Double click. It's 7 degrees, 1 minute and 15 seconds. I apologize for being rather slow in this, but I haven't done this for quite a little bit. But anyway, I hope you follow what I'm doing. Well, I appreciate your interest, and if you have further interest in this, give me a call, or that is, send me an email at duluthmsn.com. Thanks. This this is something that I've failed to show you. I go back to it. Move to excavation and VC curve. This is messages about these curves. We won't take time to look at it. Another message. Now we went and clicked for a vertical curve. Yes. We want to do a vertical curve. So we put in an approach grade, say, of 5%, and an exit grade of minus 5%, minus 5, say length of curve 1,000 feet. The elevation of the point of vertical curve, let's use 400. The station of the beginning of the curve, PVC, we'll use 1,000 for that. And let's use a station interval of 50 feet. Every 50 feet. Click on editor. And here we see the approach grade 5%, exit grade -5, PV station 1,000, PV station, PVT station is 2,000, length of curve is 1,000. We start off at station 1,000 with 400 feet. And each 50 feet, the elevation is increasing until it reaches the midpoint of 1,500 feet. And there the elevation is 412.50. And then it starts going downhill, back down to at 400. So this is vertical curves. Very simple. Thanks again. I'm sorry that I forgot to add this after I closed out the first portion of this. Thanks.